we will discuss some basics about debugging. We will look inside this black box with name debugger, and we will discover its secrets. This presentation was made thanks to these references. You can find more there, but I'm sure that after this presentation you will have a lot of information and you perhaps will be disgusted and you won't try to find anything else. While debugging, we can say that we are playing with an executable program. We can stop it, change its memory registers, then these changes we are allowed to do when the program is stopped. Then we can stop it or resume its execution. Everybody knows that the CPU executes the code very quickly. During debugging, we can execute the code at the speed observable by human senses with our sight. For playing the game, we need only one. We need another program, debugger. Why programmers need debugging? There is several reasons. This is not the complete list, only few thoughts. The first reason is to find bugs, which are critical errors causing the program crash. This is the nightmare of every assembly programmer. We do a lot of these type of errors in every program, in every project. Even if the program doesn't cause a critical crash, the procedure may still give wrong and unexpected results. And then we can use debugger to find the reason. If we have the program in fine state, then it looks without errors, then we can even use debugger to improve the algorithms. We can explore procedures, step through them, and watch what we can improve. So I am sure that everybody sometimes discovers unknown executable file in your operating system, and we are assembly programmers. I am sure you will use debugger to discover what this program has to do. Somebody may use debugger as a first step by learning assembly language. It was the same by me. I learned very much thanks to debugging. Well, debugging is possible thanks to OS operating CPU features called exceptions. What does it mean, exceptions? Exception, we can say it is something similar to interrupt. The first 32 interrupts are reserved for exceptions. Every exception foresees interrupting the program execution, and the control is given from the currently executing program to the routine handling the interrupting exception. These routines are part of operating system kernel, and they have names exception handlers. During the control transfer to the exception handler, the CPU stops execution of the program and saves its return instruction pointer, stack pointer, and flags. The handler itself is responsible for saving the rest of registers. This saving allows the CPU to restart the interrupted program at the end when the handler finishes the exception handling. Most exceptions means an occurrence of some wrong or degenerated instruction or code in the program, the nightmare of every programmer. In this case, exception boundary is reported before the wrong instruction causing the exception, and this instruction isn't allowed to complete. These exceptions are called faults. The second type of exceptions is something which we like because it makes the life complicated, but this second type of instruction of exceptions are reported on the address of the following instruction. And this second type of exception is hit just after the instruction is completed. These exceptions are called traps. The benefit of these traps is that they are the core of debugging. Some examples of exceptions everybody knows. Exception divide by 0. This exception hits or triggers interrupt 0 vector. Here are some samples. The divisor is 0, or when the result is bigger than the capabilities of the destination register. This instruction isn't allowed to complete. This is the fault type of exception. Then exception single step. This exception triggers or hits the interrupt 1. Here are some samples. It's IC EDP. It is one very unknown instruction which is not much useful. Then the second sample, when we push a flag into stack and we turn on the 8th bit, and then we write this bit into flags register by popping the flags. This is the core method of single stepping, but not in this way. This is only sample how to do it. Operating system sets this bit only in program context, and then the operating system reloads register when the task switches. You can use this sample, for example, in self-modifying or self-protecting executable. Operating system.
Interrupt for a second. The IC is a shorthand for circuit emulator. So back in the old days, you had this circuit emulator that you could attach to your processor. It was a very expensive piece of hardware, and it allowed you to do fully external debugging to the system. So really powerful stuff, and that's also why we have soft eyes, where it got its name from, because it was a software version of it. So that's where the instruction comes from.
Yeah.
One more thing.
This instruction is on, I suppose that this instruction is on the manual I show in second slide.
It's a half undocumented.
AMD doesn't have it in the instructions.
Flag assembler uses also mnemonic INT1 for this instruction.
Yeah, I know. INT1. Then we can cause exception single step by setting debug registers. Here are two samples. We just load this one is the sample of hardware breakpoint. It means that we break on instruction execution. We just load the address of instruction to execute in debug register 0, and we set only one bit in debug register 7. And then we can execute the code and wait till the instruction executes. The second sample shows how to use debug register to watch accessing memory. We just load the memory address into one debug register, and we set corresponding bits in debug register 7. And then we just wait till some instruction accesses this address. Then the interrupt 1 is triggered. Then exception breakpoint. This is the thread type of exception, just like the single step. This exception is triggered after this interrupt 3 is executed. We have two possibilities how to execute interrupt 3. This one has 1 byte and this one has 2 bytes. We will discuss later which one of them is more useful.
Although this is not question about topic, but it is question about your FDBG, your debugger. What are the main differences between your debugger and OEDebug from Hajduk?
The differences is I started this debugger because there weren't any graphical debugger for beginners for 64 bits.
Yes, OEDebug is 32-bit only.
FDBG copies the old turbo debugger. These key shortcuts and so on.
Okay, thanks.
So now the fault type of exception invalid opcode. It triggers interrupt 6 vector. Here are some samples. UD2, this is official invalid code from AMD manual. But a lot of instruction from old 32-bit world are disallowed, are illegal in long mode. And even such simple instruction like LIA can be made, can produce exception invalid opcode, because flat assembler don't allow you to compile this instruction, but you can do it manually by this way, and this goes the invalid opcode to
UD2 has been reserved in the opcode table to always produce an invalid opcode. It can be useful if you're doing some virtual machine programming to thread out to the kernel.
When instruction double fault, it is useful only in kernel, because this exception is triggered when exception is made in one interrupt handler. Then exceptions, stack fault, general protection, page fault, it concerns the kernel. Some exotic exception alignment check, it triggers interrupt 17 or 11 in hexadecimal. It is shifted.
It's an interesting exception, really.
It is a now I see a problem with transferring from one PowerPoint to another. I suppose the whole. So the third instruction is to save control 0 register into RIX, then to turn on the bit 0, the bit 18, to write this AM bit into control register 0. After this, in kernel, we can make a part in user mode program. We assume that stack is correctly aligned. crowd or double crowd. We push flags. We set the bit 18th. This is the same as in control, but now we set it in flags. Then we write it into flags, and then we try to access double word which isn't aligned at the word. This occurs only in user mode program and current privilege level 3. It never occurs in privileged software like OS kernel.
And it can be a useful thing to do if you need to check some performance, because you will be sure you only have aligned code, and it's very easy and fast to find unaligned code that way.
The whole presentation will be...
Oh, sorry.
It doesn't matter. So, how it interacts? We simplify it that we have only program, operating system, and debugger. Okay? What happens during debugging? At first, the program causes an exception. Then the CPU stops the execution of program, saves the program's instruction pointer, stack pointer, and flags, and the control is given to the corresponding exception handler or interrupt vector. Then operating system handles the interrupt vector and notifies the debugger about the exception. Here are the code of debugger. In Linux, the debugger is waiting for the message about exception in this system call. During Windows, it is this system call, wait for debug event. And in Linux system, wait for. As a fourth step, user is allowed to change registers or memory of the program via debugger. Here are the samples. The Linux system call sysptrace with get registers, set registers, peak text, or poke text. You can use these two as another. They are equal, peak data and poke data. In Windows, you can use this advanced API kernel 32 get freed contacts, set freed contacts, read process memory, write process memory. As a fifth step, the user can resume the execution of the program via debugger, thanks to these system calls. In Linux, again, sysptrace with parameter of trace continue, or other possibility which does only single step with ptrace single step. This second only just turns on the track bit of flex register, as I showed you several slides before. In Windows, it is the system call continue debug event. If the program doesn't cause any exception, then the program runs and terminates. In this case, debugger doesn't encounter any exception. This is the dream and terminal stage of developing of any program. But again, still, some procedure may give unexpected return results. So we have either work to discover it.
Very good. That's a question. Even in 64-bit Windows, do you still use kernel 32? There's no kernel 64.
Yeah, it is paradox, but the name is kernel 32. It still remains in 46 bits. It isn't error.
There are actually two versions of kernel 32. One is the 32-bit version, and one is the there's a legacy mode.
There are two shadowed directories in 46 version of Windows. One is System 42, which holds 84 bits stuff, and sys W36, which holds 32 bits stuff.
It's a bit messy.
Yeah. So, what does it mean, hardware breakpoint? This hardware breakpoint triggers interrupt one vector. And hardware breakpoint is done by setting some debug registers. There is a lot of debug registers, but we need to focus only on 6 of them. The debug register 0, 1, 2, 3, 6, and 7. These others aren't used. These 10 registers. The debug registers can be read and written only when the current protection level is 0, most privileged in kernel. Here are some samples how to set registers, debug registers. User mode debugger running at protection level 3 can access debug registers of a program when the program is stopped after causing an exception. In Linux, it is sys ptrace with ptrace get registers and then set registers. In Windows, it is kernel 32 get freed context and set freed context. By this way, we can make changes in registers of program. We just load some value into debug register 0, 1, 2, or 3 in this way. And then we need to set some bits in debug register 7 to enable this one of 4 debug registers. It isn't enough only to set one of these 4 registers. It is essentially to set some conditions in debug register 7 at the end.
Ariel, I have a question about that. Earlier you said that only certain debug registers are used. Is it possible to use them to put values in? For example, could you take what would normally be in DR7 and put it in one of the unused ones? Because you know, there's some programs that check to see if it's being debugged as a protection, and it will look for a value other than, I think it's C400 in DR7. And if it sees something other than that, it knows it's being debugged and will, protect itself. So, is it possible?
Moving into other debug registers.
Yes.
I think that most of moving in these registers causes invalid opcode or something like this. It causes another exception, but not the interrupt one. We can use only these two, debug register 4 and 5, after setting one bit in one control register. But then these one registers are only shadow copy of debug register 6 and 7.
And it's a dangerous thing if you could put data into the other registers, because in a future processor revision it could do something completely different.
I suppose that they are future, and sometime in future the others could be used for something.
Is it possible to make an exception on the reading of a debug register?
We will discuss. We will discuss it later.
Yes, I checked in Intel manuals. It's undefined UD exception.
Oh, undefined code. Yeah, that's terrible. So everything is shifted.
Oh.
So.
Existing resolution of the monitor output. Don't know if it's going to be readable on the...
So, the debug register 7. I apologize, it is shifted in a terrible way, but we can set from the easiest. To enable the debug register 0, we must enable the bit 0. Then for debug register 1, we have to enable the bit, the second bit.
How do you go out full screen mode? So
I think it's fine.
well, the problem is that it's all
100
shifted, so it's pretty hard to read.
124 multiplied by 80.
Okay, well, I don't know.
That's okay.
Sorry.
To enable the debug register 2, we need to set on the bit 4 of debug register 7. To enable the breakpoint 3, we have to turn on the bit 6 of debug register 7. This is only enabling the debug register. Then we have to set 2 other values in the debug register 7. We have to set the type and the length of breakpoint. The type means that we would like to cause interrupt 1 on instruction execution or memory writing or memory reading, or by executing the instruction in from port or out to the port. Then we have to set the length. We may set the length of 1 byte or up to 8 bytes. So for here are for setting the length, we need to set 2 bits. If both bits are 0, then the length means 1 byte. When the bit 0 is set, then it means 1 word size, and the address must be word aligned. This looks like a mistake, but this is right. In old 32 bits, this one wasn't used, and this one, when the both bits are set, were in old 32 bits reserved for double word size, and when the 46-bit CPUs came, then the developers of CPUs used this one setting to double word for 8-byte size. This is about length. Then we must set the type of breakpoint. We would like to set the breakpoint on instruction execution. In this type, we put both bits 0. Then we may want to trigger hardware breakpoint on memory accesses. We have 2 possibilities. We may want to watch writing into memory, and in this case, we set this 1 bit of the type, only bit 0. If we want to watch memory reading or writing, we have to set both bits on. And this one setting is useful only in kernel because this one watches accessing ports by in and out instructions. And this one settings is undefined until this bit in control register 4 is set. So kernel must set this 1 bit in control register 4